In artificial intelligence, data is not a secondary input, but the foundation of everything a system can do. This video explains what data truly means in AI, why it matters more than models, and how data choices quietly shape system behavior, performance limits, and real-world outcomes. AI systems do not begin with algorithms. They begin with data. Before any model is selected or trained, the structure, quality, and scope of data already constrain what the system can learn and how it will behave once deployed. Models are often reusable across problems, industries, and organizations. The same algorithm can be applied in many contexts. Data, however, is problem-specific. It reflects a particular environment, population, and measurement process that cannot be easily transferred. When the same model is trained on different datasets, the outcomes can differ dramatically. Performance, bias, reliability, and usefulness all change. This is why experienced practitioners focus first on understanding data before adjusting models. Data defines the boundaries of what an AI system can know. If something is not present in the data, the system cannot learn it. These boundaries are often invisible but decisive. Data consists of observations about the world, not the world itself. It is a representation created through measurement, recording, and selection, which always introduces simplification and loss. Observations come from sensors, human input, digital systems, and institutional records. Each source captures certain aspects of reality while ignoring others. The process of turning reality into data is inherently lossy. Many details, contexts, and causal relationships are discarded in order to produce structured records that machines can process. Because of this, data is always an approximation. It reflects what was measurable, observable, and considered relevant at the time of collection. Data is also contextual. The same variable can mean different things depending on how, when, and why it was collected. Raw data becomes information when it is cleaned, organized, and structured. Information becomes knowledge only when patterns are learned and generalized. AI systems operate at the level of learned patterns, not understanding. They transform data into statistical regularities, not meaning. This distinction explains both the power and the limits of AI. Systems can detect subtle patterns at scale, but lack awareness of what those patterns represent in the real world. All real-world data is imperfect. There is no such thing as a clean, complete, or neutral dataset. Noise refers to random variation or irrelevant signals present in data. Noise can obscure useful patterns and mislead learning systems. Missing data occurs when observations are incomplete or unavailable. Missingness is often systematic rather than random. Measurement errors arise from faulty instruments, inconsistent procedures, or limited precision. These errors propagate into models. Human errors include incorrect inputs, inconsistent labeling, and subjective judgments. These errors reflect real human limitations. Data reflects processes that generated it, not objective truth. Understanding those processes is essential for interpreting model outputs. AI systems learn correlations, not causation. They identify statistical relationships without understanding why those relationships exist. This is why AI systems can appear confident while being wrong. Confidence scores reflect data patterns, not correctness. Between the world and data lies a translation layer, sensors, forms, interfaces, and rules that determine what becomes visible. These mechanisms shape the dataset. What is easy to measure is often overrepresented, while complex realities are excluded. Visualizing the mapping from reality to data helps reveal where information is lost or distorted. Consider medical datasets. They often contain test results, diagnosis codes, and treatment records. What they capture well are standardized procedures and measurable indicators. What they miss includes patient experience, social context, and unrecorded symptoms. Absences in data matter. What is not recorded can be as important as what is present. Every dataset has boundaries. These boundaries define who is included and who is excluded. A common misconception is that more data always improves models. Quantity does not guarantee quality. In some cases, more data amplifies existing biases or reinforces outdated patterns. Data also changes over time. Behavior, environments, and institutions evolve, causing data drift. Static datasets struggle to represent dynamic realities, leading to degraded performance. AI systems can influence the world, creating feedback loops that reshape future data. Labels impose definitions on reality. These definitions shape what the system learns as truth. Early data decisions are difficult to reverse. They create long-term constraints. Data debt accumulates when poor data choices require increasing effort to correct later. Many model failures originate in data problems rather than algorithmic ones. Effective debugging begins by inspecting data, not tuning models. Data is a design choice. It reflects priorities, assumptions, and trade-offs. Engineers and organizations shape data intentionally or unintentionally. Ethical considerations begin with data collection long before model training. Fairness is constrained by what data represents and omits. There is no perfect data set, only better or worse trade-offs. A practical mindset treats data as something to question, not trust blindly. Key questions include who generated the data, how it was collected, and why. Data literacy is therefore a core AI skill. The central takeaway is simple. Data defines what AI can and cannot do. Models follow data. They cannot transcend its limits. Next, we examine the major types of data used in AI systems and why they matter.